And here's the lattice. And what you can see is that in each period, there are two parameters. This is a typo here. There should be an equal sign. RU is equal to. And you'll notice that in each state, there are two parameters. There's an RH factor. So in this, in the first step, we have an RH and a sigma 1. In the second column, we have an R2H and a sigma 2. Notice that in each step in the lattice, there's only one sigma. And the same sigma is used throughout that column. And notice the coefficients of sigma. We go from the RH, which is the base rate. RH is going to help us set the level of interest rates, and that's what's going to help us price our bonds. And then from there, the volatility is going to go from, notice we have RH, then we have e to the 2 sigma, and then e to the 4 sigma. In other words, at each step on the lattice, this is a recombining lattice, unlike the earlier one. There's an advantage of this. It's combinatorially simpler to work with. It's a recombining lattice of short rates. And notice that at each step, in each state, we actually are implementing 2 sigmas. So we go from the R interest rate, and then we use R, and we use e to the 2 sigma 2 square root of h. Notice the square root of h factor. And when we, because these are annual interest rates, we'll need to multiply them by h when we use them. And then in the final period, again, we have a sigma 3 and an R3H and a sigma 3. And in each step, they go up by 2 sigma, 4 sigma, 6 sigma, and that's how it works. So it's the Black-Derman-Toy. It's a short rate model, as we just saw. Each period, as I indicated, has 2 parameters, an R rates that gives you the level in that column, and then the sigma I, which gives you the variability of the rates by state. And we're going to use these parameters to match the data in that table. So first of all, let's make sure we understand what yield volatility means. I described it intuitively. Here's the math. So using familiar notation, this is the price at time h of a bond maturing at time t, where the short-term rate is RH. So here we have, here's our timeline. We're at time h, and we're looking at a bond that matures at time t. If I have the price of the zero coupon bond at time h, namely the price of a bond that pays $1 at time t, then I can just reverse the calculation and get the implied yield. And I note here that this is an annualized yield on the bond. It's not a continuous yield. You'll notice just the math we're using is we're taking a root of the price, subtracting 1. So this is just an annual model of interest rates, and we certainly could do this using an exponential or a continuous model. There's no need to do so. This is a perfectly legitimate way to model interest rates. We'll just need to remember that these interest rates are not continuous when we go to use them later. The yield volatility then is 1/2 the log of the ratio with this factor. This formula may look a little unusual, but what it basically tells you, if you just reverse this, and I call this sigma, what it tells you is that the yield in the upper state is equal to the yield in the lower state times e to the 2 sigma square root of h. So this is the reason that we have the rates go up by 2 sigma. And it may look unusual to you, but you may want to remember that in the stock model, we had an e to the plus sigma square root of h here, and an e to the minus sigma square root of h here. So although numerically it was disguised, in our stock lattice, because we had a plus and a minus sigma in the stock price evolution, Indeed, as we moved up in states in our lattice, we were picking up 2 sigma at each step. So this is doing exactly the same thing, but just notationally gets away from the plus and minus sigma, and instead works with 0, 2 sigma, 4 sigma, and you could argue that the first minus sigma is buried in the fixed term RH, and then from that RH adjusted value, it's all the same. But you'll notice that we've always been dealing with 2 sigma steps per state. It just was disguised because it looked like we had a plus or minus sigma and it looked like 1. But going from minus to plus is actually a 2 sigma adjustment. And so that's what we have here, that volatility has the property that whatever state you're at, the one above it has to be e to the 2 sigma root h times the one below it. And that's why our lattice goes up by multiples of e to the 2 sigma.